Astronomers are facing a claim that should be impossible. Harvard astrophysicist Avi Loeb has pointed to the newly designated A3i Atlas, an interstellar object inbound on a hyperbolic path, and noted that within just 116 days it will sweep past the Sun at a distance not far beyond Earth's orbit. Officially, the story is calm, a faint comet, icy, unremarkable, never closer than 1.8 astronomical units from Earth. But the timing is what unsettles researchers. The odds of such a body arriving so soon after ʻOumuamua and Borisov are vanishingly small. The baseline of orbital statistics doesn't match the official calm, it matches an anomaly. Experts split between reassurance and alarm. Some call it a routine cometary pass with wide margins. Others whisper about precision trajectories and engineered timing. Accident, mission, or intervention? The debate is open, the evidence is thin, and the stakes could not be higher. This is where the mystery begins. A3i Atlas is inbound. Its arrival cannot be delayed. And the question no one can yet answer is simple. What exactly is heading for us? The first record of A3i Atlas came through the Minor Planet Center, flagged by the Asteroid Terrestrial Impact Last Alert System. On Discovery images, the object appeared faint, magnitude 18, drifting against the background stars of Sagittarius. Follow-up measurements from the Pan-STARRS network confirmed what the initial orbit hints already suggested. This was no bound comet, but a hyperbolic interloper. A designation was quickly issued. A3i Atlas, the third confirmed interstellar object after ʻOumuamua in 2017 and Borisov in 2019. Both predecessors had stirred debate. ʻOumuamua, with its elongated profile and unexplained acceleration, prompted Avi Loeb to propose an engineered origin, an idea that drew international headlines and fierce skepticism. Borisov, by contrast, behaved like a classic comet, shedding gas and dust in familiar patterns. Atlas sits uneasily between them. Its orbital eccentricity matches interstellar origins, but its brightness curve and compositional oddities already defy the template. That is why Loeb, still director of the Galileo project at Harvard, returned to the conversation. If A3i Atlas follows its projected course, the object may become far more than an academic case study. It could become a direct concern for Earth. Hyperbolic visitors are not just rare, they are nearly non-existent. Before 2017, no confirmed interstellar object had ever been observed passing through the inner solar system. Billions of years of planetary history without a single detection. Then, within less than a decade, three appear: ʻOumuamua, Borisov, and now Atlas. Statistically, this is a cluster event. The odds of three inbound trajectories arriving so close together in time are vanishingly small. Most comets we observe are long-period objects. They return on cycles spanning tens of thousands of years. Their perihelia scatter across centuries, arriving, unpredictably but always spread thin across the timeline. What they do not do is arrive in synchronized pairs, much less in tandem with interstellar bodies. And yet Atlas is not arriving alone. Just weeks before its confirmation, C-2025 R2 Swan entered the watch lists, sweeping a colossal tail across Virgo. The geometry is striking. Two bright, anomalous bodies inbound within the same 10-day perihelion corridor. By chance alone, the separation between such arrivals should be measured in centuries. Instead, the two most unusual objects of the decade converge in the same season, their approach vectors tilted steeply against the ecliptic. The improbable choreography suggests a deeper question: random coincidence, or something else? Mainstream models note that interstellar detections are expected to rise with improved surveys like Atlas and Pan-STARRS, but the clustering of three within a decade still pushes the boundaries of probability. Orbital solutions published through the MPC place A3i Atlas on a hyperbolic arc with an eccentricity greater than 1.2. Its inbound velocity relative to the Sun exceeds 26 kilometers per second, consistent with interstellar origin, but it is the projected close approach to Earth that ignited debate. Extrapolated ephemerides suggest that by mid-January, just 116 days from the present, its uncertainty corridor overlaps Earth's orbital path, though current MPC solutions indicate the closest approach remains more than 1.8 AU away. The calculation is not a prediction of collision. The error bars remain large, and ongoing tracking will refine them. Still, Avi Loeb points out the corridor is uncomfortably aligned. For an interstellar body discovered so recently, the statistical window should be much wider. Instead, Earth sits inside the margin. That raises questions not about certainty, but about possibility. Loeb emphasizes that mainstream dynamics place Atlas safely distant, but he highlights the statistical oddity of its orbital alignment with Earth's corridor. Even mainstream orbital dynamicists concede the error ellipse cannot yet rule out a close pass. The key date is fixed, 116 days until potential intersection. The outcome depends on updated astrometry, but until the blackout ends and fresh data arrive, the object's trajectory remains partially unresolved. Visualization maps show the line of variation threading Earth's orbit with unsettling precision. Whether the crossing is harmless or hazardous, the countdown has already begun. As 3I Atlas draws closer to perihelion, its solar elongation, the angular separation from the Sun as seen from Earth, steadily shrinks. Atlas will be unobservable in optical wavelengths for much of October due to solar conjunction, with the blackout window stretching roughly from October 1st until early November. In other words, during its most active phase, heating, tail development, possible outbursts, or non-gravitational forces, Atlas will be hidden behind Sun's glare. The region of the sky where it passes will effectively merge with daylight, blotting out critical positional updates and brightness measurements. Without real-time astrometry during this stretch, orbital solutions carry elevated uncertainties. This solar conjunction window overlaps the predicted perihelion date, October 29th, meaning the moment of closest solar approach occurs inside that observational blind zone. Any sudden acceleration, fragmentation, or shift in trajectory at closest approach would remain unobserved until the Sun's glare recedes. Once Atlas emerges again, the path may have shifted, the tail may have changed, or unexpected dynamics may have taken place. But for weeks, we're forced to track it on extrapolation, not fresh measurement. That presents a wedge of uncertainty during the exact period when clarity matters most. Spectrographic surveys from multiple observatories quickly revealed that 3I Atlas was not behaving like a standard comet. Early spectra indicated a dominance of nickel emission lines with an almost total absence of iron. That finding alone set off alarms. Nearly every comet studied in modern astronomy shows a blend of nickel and iron in vaporized traces. A body rich in nickel but stripped of iron challenges existing models of cometary chemistry. The anomalies did not stop there. Instead of the classic water vapor signature that dominates most comet comi, Atlas showed an unusual mix. Carbon dioxide emissions surged at rates nearly 5 times stronger than water. The 4.3 micron CO2 line dominated, while H2O barely rose above instrument noise. Such CO2-heavy profiles are rare, though not unheard of in comets formed at the coldest edges of protostellar disks. Mainstream explanations point toward calibration issues or unusual formation histories. Some teams suggested that early spectrographs were misaligned, producing misleading line strengths. Others argued that an extreme cold origin environment could plausibly yield a CO2-dominant body. Yet, even after independent reviews, the nickel-to-iron imbalance remained unresolved. For some, it was a glitch. For others, it was a signal. The Atlas anomaly file remained open, and the questions it raised only deepened with time. While the composition raised eyebrows, the motion of Atlas unsettled them further. Observers tracking its brightness and orbital curve reported a pattern that did not match standard cometary outgassing. Instead of smooth acceleration from solar heating, the object displayed abrupt jumps, stepwise changes in velocity. These delta pulses appeared roughly 2 weeks apart, each accompanied by a sharp change in the color of the tail. The first pulse was logged in late July. Photometry showed a sudden brightness increase, while the spectral slope shifted from a reddish hue to nearly neutral. By mid-August, a second pulse repeated the sequence, this time with even greater magnitude. The cycle repeated a third time. In early September, with brightness surges echoing the same pattern. Natural outgassing produces irregular flares, but rarely with such timing and regularity. Each acceleration was sharp, rising within hours, then fading as if a controlled burst of energy had been applied. When researchers estimated the force required to generate these shifts, the numbers pointed toward an internal energy source on the order of 10 gigawatts. That is equivalent to 10 modern nuclear power plants operating simultaneously. Mainstream astronomers caution against drawing engineered conclusions. They cite hidden jets, unknown ice compositions, or systematic data errors. But the rhythm and magnitude of the pulses remain difficult to reconcile. A speculative hypothesis began circulating in forums and preprints: thrust modulation, a mechanism not random but timed, not born but possibly built. If Atlas alone raised doubts, its timing alongside C-2025 R2 Swan forced astronomers to reconsider chance entirely. Swan, discovered just weeks earlier, displayed a tail stretching more than 2 degrees across the sky, 5 times the width of the full moon. Its brightness surged quickly into naked eye range, making it one of the most vivid comets of the century. Individually, either Swan or Atlas would have been notable. Together, their choreography defies expectations. Orbital calculations show Swan reaching perihelion around October 20th at a solar distance of 150 million kilometers. Atlas crosses perihelion on October 29th at a distance of about 1.36 AU from the Sun, while Swan peaks around October 20th near 1.0 AU. That places their perihelia within just 50 million kilometers of each other, closer than Mars ever comes to Earth. The geometry is striking. Swan approaches on a steeply inclined orbit more than 60 degrees off the ecliptic, while Atlas arrives from nearly perpendicular to the planetary plane. Their entry vectors originate from widely separated regions of the sky, yet both objects converge in the same narrow corridor within days of one another. By chance alone, this alignment should be measured in millions of years, not a single decade. The coincidence is sharpened by timing. Both objects reach their solar encounters during the October blackout, when ground-based telescopes are blinded by the sun. 2 anomalous bodies overlapping in space and time, hidden during their most active phase. The geometry does not prove intent, but it is enough to trouble even the most cautious skeptics. Avi Loeb's voice carries weight because he has stood here before. In 2017, when ʻOumuamua slipped through the solar system, Loeb argued its unexplained acceleration could point to artificial origin, perhaps a light sail or probe. The claim ignited controversy, dividing the astronomical community between traditionalists and those open to engineered explanations. Today, Loeb directs the Galileo Project at Harvard, a program dedicated to systematic searches for interstellar technology. When he warns that 3I Atlas could be more than natural, the statement is not casual. Loeb has suggested Atlas may represent a controlled mission. 3 speculative frameworks circulate around his remarks. The first is a solar pit stop. In this view, Atlas and Swan are probes timed to skim the sun for recharging or data relay, exploiting solar magnetism as a natural power node. The second is intervention. If one probe had malfunctioned, a second could arrive to rendezvous, recover, or neutralize it. That would explain dual arrivals in a single corridor. The third is escalation. ʻOumuamua in 2017, Borisov in 2019, and now Atlas and Swan could form a chain of increasingly complex probes responding to Earth's century of radio leakage. Loeb stresses these are hypotheses, not proofs. Mainstream astronomers still favor natural origins, rare coincidences, exotic chemistries, or observational errors. Yet the anomalies keep stacking. Nickel dominance, CO2 heavy outgassing, delta pulses, synchronized perihelia. Each new data set narrows the line between coincidence and pattern. Loeb's position is clear. Atlas cannot yet be dismissed as just another comet. It may, at the very least, be something designed with intent. Long-period comets do not just intersect astronomy, they sometimes intersect human history. Ice core records from Greenland and Antarctica show chemical spikes and dust layers that align with major comet passages thousands of years ago. These sudden atmospheric disturbances may have left imprints not just in climate, but in memory. One of the most intriguing sites in this discussion is Göbekli Tepe in southeastern Turkey, a monumental complex built over 11,000 years ago. Among its pillars are carvings of animals and abstract celestial motifs. A handful of researchers have proposed that some of these symbols may represent bright comets or even specific alignments in the sky. The hypothesis suggests ancient observers were recording cycles of rare long-period visitors, potentially even ancestors of objects like Swan or Atlas. Mainstream archaeology, however, urges caution. Most experts argue that such interpretations are speculative pattern matching, with no direct evidence linking the carvings to astronomical cycles. The carvings could just as easily symbolize myth, ritual, or seasonal change. Still, the resonance is powerful. If Atlas truly follows a trajectory spanning tens of thousands of years, its last passage might have coincided with moments when humanity first raised monuments to the heavens. Coincidence or continuity, the suggestion places today's sky watchers in a chain of observers stretching back to the dawn of civilization. Official channels have not matched the urgency of independent observers. Internal schedules from both the European Space Agency and U.S. Space Command list October as solar conjunction downtime, but sources close to telescope allocation boards describe something stricter: direct orders to suspend high-resolution imaging and radar coverage of both Swan and Atlas during the blackout, Requests for raw data, normally routine, were reportedly delayed or rerouted. Alternative proposals for partial monitoring with side-looking instruments were denied without explanation. In effect, during the most critical weeks, the public record goes silent. That silence has not stopped amateurs. Bill Gray, a veteran known for open-source orbit predictions, rallied a distributed network of backyard astronomers and small observatories. Using wide-field CCDs and improvised tracking software, they pledged to monitor every flicker that escapes the blackout. In Spain and Portugal, the Ibero Collective pooled wide-field sensors. Leaks from private groups hinted at plans to repurpose small radio dishes and even weather satellites to bypass the official silence. Suspicion lingers that agencies know more than they admit. Whether the restrictions are security precautions, calibration concerns, or something deeper remains unclear. For now, the clearest data stream may not come from governments, but from scattered independent telescopes pointed skyward. Skywatchers still have opportunities, before and after the conjunction blackout, to catch Atlas and Swan in action. Though Atlas moves into a low elongation zone by early October, in late September, observers should aim toward the western dusk sky just after sunset. Its brightness may reach magnitudes in the 9 to 11 range, visible through mid-sized amateur telescopes under dark skies. Swan, by contrast, is expected to brighten more aggressively, perhaps reaching near naked-eye visibility in October. Its tail may stretch several degrees, best captured from dark sites with wide fields. Use low magnification, wide-view eyepieces or binoculars to maximize tail coverage. Once the solar conjunction window begins in early October, lasting through early November, both objects will slip too close to the sun's glare to be observed from Earth. After the glare subsides, reacquisition will be critical. Observers should plan for first post-conjunction imaging sessions immediately as dawn or dusk returns them to view. Be ready to compare positions against old ephemerids, looking for deviations or unexpected brightness changes. Recap: 2 anomalous visitors, Atlas and Swan, approaching in the same season. Atlas's composition and motion deviate from standard comet behavior. The conjunction blackout will obscure the critical perihelion phase, and Avi Loeb's warning rings in this context. If Atlas truly lies on a potential Earth corridor, we may not know until after the moment of risk. 116 days remain until Atlas reaches its potential intersection path. If it is heading our way, the first verifiable signal will not come from an official announcement. It will come from someone quietly watching the sky,